Classical physics treats the continuum as pristine. We assume the substrate is perfectly reversible, a smooth manifold where energy dissipates without leaving a physical trace. Applied physical systems rarely maintain this idealized symmetry. When fields interact at high intensities, they deviate from the clean mathematics of smooth gradients. We observe that as structures dissolve, they fail to erase themselves from the background. They leave behind measurable inconsistencies. These imprints appear as ghost fields, hysteresis, and topological tears. In the UHS framework, these residuals are called the shadow. They represent the physical limit where our standard continuous mapping equations cease to function. Rigorously defining the shadow involves identifying the exact coordinates where the assumption of a differentiable manifold fails. These localized mathematical failures correspond to the points where abstract energy distributions settle into permanent, rigid boundaries. To understand how systems actually persist, we must look past perfect dissipation and calculate the topological scars left behind in the continuum. First, we begin with the ghost field. This plot tracks an active attractor basin. Standard models assume once the driving field drops to zero, the region should return to its original flat configuration. The driving field vanishes, yet the 3D topology retains a faint, shaded phantom boundary. The continuum remains warped. Complex continuous media possess structural memory. They record the influence of past interactions. This memory is formalized in equation 1301. The current state, MFT, integrates its entire interaction history. Because this recorded history is finite, the system cannot return to a zero state. The equation resolves to a non-zero remnant. This remnant is a ghost well, a localized hysteresis scar in the substrate. This invisible warp conditions the environment. It acts as a structural precondition for any new formation. A system's history dictates how easily future structures can form in that location. The continuum possesses an indelible memory. Structural memory explains how fields dissipate. A different anomaly occurs when active fields collide. Consider two distinct wave fields expanding toward one another. Their internal facelines are color-coded to track specific symmetries. At the moment of collision, these internal symmetries rarely align. This mismatch creates a localized point of high contrast. Standard manifold mathematics relies on smooth, differentiable phase transitions from one point to the next. This mismatched collision breaks that requirement. The phase lines cannot be reconciled into a smooth gradient. We quantify this breakdown by calculating the winding number, end, using a contour integral. Tracing a path around the defect shows how phase angle theta changes. In a smooth field, this sums to zero. Here, the result is a non-zero integer, identifying a singularity. At this coordinate, the phase of the field can no longer be defined. This is a topological defect, a tear in the fabric of the continuum. These mathematical tears become permanent physical boundaries. They trap structural coherence in localized knots that fundamentally resist dissipation. The final topological residual is the fold catastrophe, also known as a magnetic switchback. In this plot, gradients determine how fields align, depending on the consistent curvature of the landscape. As long as curvature remains smooth, the field adjusts linearly. But if the second derivative of the potential vanishes and changes sign, local curvature disappears. The landscape folds. This event represents a total collapse of the smooth gradient assumption. Forced into this topological switchback, the field undergoes a sudden, nonlinear state transition. These unexpected folds demonstrate that the continuum periodically forces radical phase shifts rather than allowing infinite, smooth change. This aggregate view reveals a mature continuum as a massive, organic landscape of deep history and physical memory. Every system's current energetic state is constrained by the topological scars left behind by previous interactions. These lingering ghost fields, topological field tears, and fold catastrophes function as non-eradicable physical boundaries within the substrate. Accounting for these boundaries requires a specific engineering posture called epistemic humility. Rigorous models must explicitly acknowledge the failure points of their own continuous mapping assumptions. We enforce this using the three-ledger check. This protocol ensures that theoretical explanations respect structural coherence and empirical plausibility. Mapping the shadow reveals how the localized failure of pristine equations produces the permanent, measurable structures of our reality.